Okay, these things are also very important, that has to be taken into picture, that we usually skip. Now I'm quickly going through. See, I will repeat this one, how to wire discrete sensor, because this is in line to this. Just I was showing that how you connect a particular sensor to PLC and why PNP and NP are required. I have taken it earlier, but a correct line of action I have just managed to do a correct line of videos. So I will just paste it on a Word and make a document in front of you, so we will be aligned to the knowledge path. This will be the very correct knowledge path. First we have gone through the type of sensors, then we will go about the PNP and NPN sensor, then about wiring, and then about photoelectric sensor. So we have covered type of sensor, now we are covering inductive sensor. Just have a look at this. uh, I'm not presenting. I think I'm not presenting, right? Yeah, I'm not presenting. My bad. Sorry. I was not presenting. Yeah. So what I was saying is that I had gone through the type of sensor. Now I will go with inductive sensor, and this how to wire I will repeat. Okay. So just have a look at this.
Here is what an inductive sensor looks like. These are produced by data logic and are commonly used in automated processes. There are many shapes, sizes, and applications for inductive sensors. Most commonly, they are used as metal detectors and proximity sensors. You probably interact with a multitude of inductive sensors every time you pull up to a red light. Arrays of large-scale inductive sensors are how many traffic systems determine how many cars are waiting at a red light. That's what those strange patterns and shapes are on the road at intersections. In automation, they are regularly used to sense the presence of a metal part and send that information to a programmable logic controller. An inductive sensor is a non-contact sensor that uses a coil and an oscillator to generate a magnetic field around the sensing surface. When a metallic object enters the operating area of the sensor, there is a dampening of the oscillation amplitude, which is read by a threshold circuit and changes the output. Any object that isn't metallic won't interfere with the magnetic field that is generating around the sensing surface. The detection range of the sensor greatly depends upon the type of metal being detected. Ferrous metals like iron or steel will increase the detection range, while non-ferrous metals such as copper or aluminum will decrease it. Since inductive sensors cannot measure the distance or size of an object, they are sometimes described as an inductive switch. Their output can only be on or off. Let's take a step back. What is a switch? A switch is a device that can make and break the connection in an electric circuit. We use switches every day, from typing on a keyboard to turning on the lights in your home.
Please get focused on this part, that how they are transforming it, because it is important. It might look simple at this stage, but when we connect it to each other, it gets tough. So just focus on this part. It is very important.
Connection in electric circuit. We use switches every day, from typing on a keyboard to turning on the lights in your home. There are two categories that all switches fall into: maintained or momentary. Simple light switch on the wall is a maintained switch, meaning it will remain in one state until actuated into a new one. Each actuation of the switch will change its state. The switch will maintain the on or off state that you last set it to. Maintained switches can be referred to as toggle switches. An inductive switch is a momentary switch, meaning it will only change its state while actively triggered. Once the object that triggers the switch leaves its operating area, the switch will return to its normal state. Momentary switches are sold with an output of normally open or normally closed. This refers to the default state the switch will be in when it isn't actuated. When purchasing an inductive proximity sensor, you must choose between normally open and normally closed. Think of the letters on a keyboard. Each one of them is a momentary switch, and its normal state is open. Only when that key is pressed will the state of the switch change to closed. Immediately after releasing the key, it will default back to its normal state of open. You don't have to press each letter twice to toggle it on and off. The state of the switch is changed momentarily while actuated. On top of deciding between normally open and normally closed, you must also decide between an NPN or a PNP transistor. These control the current flow within the sensor. This diagram shows a basic NPN transistor in a circuit. Currently, this is an open circuit. When we close this switch here, the current now flows from the positive terminal through a resistor and into the base of the transistor. The low current switches.
Class, very important thing for you, your output is here. Okay, just look at the output and how your this circuit is going to work. Okay, your output is here, just have a close look at this only.
Transistor on. Same current will continue to travel through the emitter, ground, back to the negative terminal to complete the low current loop. Now that our transistor is switched on, we have a larger loop that becomes active. A higher current will now flow from the positive terminal into the collector. From there, it is shunted to the emitter since the transistor is now on, travels through the ground, and heads back to the negative terminal. If we were to add an output to the circuit, it would be between the positive terminal and the collector. This diagram shows this.
It is an important exercise, that is why I'm doing this. Okay, class, now just have a close look. This kind of sensor is the screen visible? Is the NPN sensor completely visible to all of you? I have to look at your answers also. That is why I'm doing this practice. Theater mode. Yeah, theater mode will work. Okay, this is a sensor of what kind? This is a sensor of what kind? PNP or NPN? NPN. Now, it might look easier for you, but um, I've already told you that it is important that how you look at to the sensor. Now you can see your sensor is this, okay, and your output is this, okay. So the current is passing from the output to the collector, okay. So it is passing because when the switch is on, and the switch is on by activation, whenever there is an activation, the collector will take the current, okay. The collector is going to get the current, okay. So it is very important for you to understand that how this function works. Now you understood that what is the process. Yeah. The important thing was that from output the current will be passing. So if output is a PLC, okay, if output is a PLC, then what will happen? The PLC should be sourcing or sinking. Current will be falling from sourcing. Sourcing, it will be sourcing, okay. Why it will be sourcing? Because current is moving from an output to the sensor, okay na. So NPN sensor is a sinking type of sensor and it will be sourcing. It might look easy for you, but let us continue, and please kindly focus on this because it is very important for you to focus on this concept, okay, because in line we are going to move with other videos.
Same circuit, the PNP. Although less common than NPN, they function similarly. The difference is that in a PNP circuit, current flows out of the base to turn the transistor on, compared to the NPN circuit, current flows in. That is why PNP is called sourcing sensors, since they source positive power through the output.
PNP sensors are sourcing sensors, NPN sensors are syncing sensors. PNP sensors are sourcing sensors that are connected to syncing PLC, and PN are syncing sensors that are connected to sourcing PLC or sourcing output. Okay?
Ground. That makes these transistors complicated. In NPN inductive proximity, the output will be high, low when it detects a metallurgical amp. PNP will be the exact opposite. Or picking one or the other, make sure they are compatible with the PLC. You are looking for a sensor that can cover proximity, distance, position, placement, material type, humidity, liquid levels, and more, then you may need a capacitive or a photoelectric sensor. Thanks for watching. If you have any questions, please post them in the comments. We will do our best to answer. If you enjoyed this video, be sure to subscribe to Lecture4b.
Okay, now let us have a very quick look to how to wire this. Now you understood it, how NPN and PNP sensors are different. Now let us go to this.
Wire DC sensor, like an inductive proximity sensor to a PLC input card. You'll also learn what a 3-wire discrete sensor is and recognize some of the common types of 3-wire discrete sensors. Before we start this video, I have a favor to ask. DC sensors can be used to indicate the state of a device or a process to the PLC program. Knowing these input states can allow the PLC program to make decisions, such as when to start or stop a conveyor motor. In this diagram, the programmable logic controller, or PLC, is running a ladder logic program. The inductive proximity switch is connected to a PLC input card, and the logic program is written to sense the state of the switch. For instance, when a box is placed on a conveyor at the loading position, the proximity switch senses the presence of the box and commands the conveyor motor to start to transport the box to the next inspection station. So, let's see how we can make this important discrete sensor input information available to a PLC program. In order to do this, we need to understand more about these discrete sensors and how they are wired to the PLC. Discrete DC sensors, or discrete direct current sensors, operate in a circuit with a battery or other power source, commonly known as a power supply. A power supply is placed in an electrical circuit to provide power to the connected devices, like proximity switches or a motor. DC power supplies are referred to by their voltage and capacity, indicated by how many amperes they can supply. The more amperes a power supply can deliver, the larger and more expensive they generally are. In DC PLC circuits, the power supply almost always supplies 24 volts DC to the connected devices. In this diagram, a DC circuit is shown, which turns on a motor when a proximity switch senses the presence of a part or an object in a specific location. The common trait of all discrete DC sensors is that they have exactly 2 operating states, on and off. A discrete DC switch, as in this diagram, is on when an object is in proximity to the switch and its internal contact is closed, forming a complete circuit and allowing the flow of electrons. When the object is moved away from the proximity sensor, its contacts are opened again. The circuit is broken and the flow of electrons stops. The state of the switch is off. Other common examples of discrete DC sensors include many other types of proximity sensors, level switches, pressure switches, and photoelectric sensors. If we want to monitor the state of a proximity sensor in the PLC, we would need to connect the 3 wires of the proximity sensor to a digital input card in the PLC. When the proximity sensor does not...
Now, I know it is repetitive, but I am repeating it because intentionally, because it is very important for you to go into line of this learning path, that how NPN and PN were sourcing and syncing, and how it is connected to PLC. Because if it is clear in your mind at this point of time, that it is going to be very much beneficial for you. Okay, you can answer it very confidently during your interviews also, that I know and I can draw it in front of you that how I connect. And if you are yourself are going to answer this question in front of any industrial expert, any industrial person, he is definitely going to recommend you.
sense a part nearby, the PLC would see the input state as off or a 0. The circuit to and from the PLC input is open or not energized. When a part moves in front of the proximity sensor, the PLC input senses the change in state and transmits this data through a communication channel to the processor memory or data table. When the proximity sensor senses a part nearby, the circuit to and from the PLC input is closed or energized. We could then write a PLC program which resides in the memory of the PLC to take some action, like starting a conveyor motor when a part is near the proximity sensor. Wiring a discrete DC sensor to a PLC input card is easy and straightforward. In this video, we will consider only devices that have 3 wires that need to be connected to the PLC digital input card. An example, an inductive proximity switch, is shown here. In a separate video, we will consider some simpler 2-wire devices. For most PLCs, the input cards must match the type of circuit that will be employed to interface the device to the PLC. For example, a discrete DC device must be wired to a discrete DC input card. A discrete AC device would require a discrete AC input card. In this video, we will consider only DC devices. In order to connect a 3-wire discrete DC device to the PLC, we will need to identify whether the device is an NPN or a PNP type. NPN and PNP are 2 types of bipolar transistors, which are simply solid-state switches. You should always check the manufacturer's data sheet for the device you are going to connect to the PLC to make sure you know its configuration. For now, just remember the NPN switches are referred to as syncing, and PNP switches are referred to as sourcing. Note that each of these...
Now you know that how PNP switches sourcing and how NPN switches syncing. Okay? Because we have aligned these 2 videos.
Sensors has 3 wires. Wire 3, the black wire, is always connected to the load, which is the terminal for an input on a PLC digital input card. In this simplified diagram of an inductive switch, there are 3 wires, 1 brown wire, 1 blue wire, and 1 black wire. The standard convention is that the brown wire is connected to the positive side of the power supply, plus 24 volts DC, and the blue wire is connected to the DC common terminal of the power supply. This is the negative terminal that is present on the power supply. The black wire is the output, or load wire, of the sensor. It gets connected to the PLC input terminal. Earlier, we said an NPN sensor was referred to as a syncing switch. This means that the load, which is the PLC input, is wired as shown in this diagram. Notice that plus 24 volts DC is wired to the PLC module's common terminal. In other words, when the switch changes state, it syncs the load to common or ground. For many PLC manufacturers, connection of NPN sensors requires a specific model number for the digital input card. Because NPN sensors are syncing, they require a sourcing type PLC input card. A PNP sensor is referred to as a sourcing switch. This means that the load, which is the PLC input, is wired as shown in this diagram.
Yeah. So class, this is a PNP type of source, okay? And this black wire, what kind of load it will be giving? Will it be 24 volt? Whether it will be 0 volt? Tell me. Okay, 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 okay. Had it been an NPN switch, then tell me this wire would have been of what? Okay, this wire will always be connecting to this, uh, this blue wire. Okay, this is a blue wire. Okay, this wire will be connected to this, and this wire will be connected to plus or minus if it would have been an NPN. Just forget about the color. Okay, don't go for color coding. If it would have been the NPN switch, then this wire would have been connected to, this is a common wire which has been connected to your PLC, and this, yeah, this would have been connected to plus. And yeah, so one more thing that you need to understand is that this common is connected to negative when it is a PNP switch, and this common is going to get connected to positive whenever there is connected to positive whenever there is an NPN switch. Okay, now I think, yeah, for NPN switch. Yeah, correct, Muskan, correct. Ankush, Aprajita, yes, correct, very much correct.
Notice that the blue common wire is connected to the PLC module's common terminal. In other words, when the switch changes state, it sources or supplies plus 24 volts DC to the PLC input. For many PLC manufacturers, connection of PNP sensors requires a specific model number for the digital input card. Because PNP sensors are sourcing, they require a syncing type PLC input card. Because NPN sensors sync voltage and PNP sensors source voltage to the PLC input, NPN and PNP sensors should never be mixed on a PLC input card. Doing so can lead to an unsafe condition. In this diagram, an NPN and a PNP sensor are both connected to the same PLC input card. Note that the common terminal has a brown wire from the NPN sensor with plus 24 volts DC connected to a blue wire from the PNP sensor, which would short the power supply to ground. Now, let's see how 3-wire discrete DC sensors are connected to actual PLC I/O cards. This is a schematic of one model of Siemens SM321 digital input card, part number 6E73221-7BH01-OABO. It is a 16-channel, 24-volt DC digital input card that is very popular in Siemens PC S7 and S7 300 PLC systems. This digital input card wiring scheme is similar to most digital input cards used in the process industries. The SM321-7BH01 has 20 screw terminals to which the digital inputs are connected. As we saw previously, for 3-wire discrete DC sensors, each digital input channel requires the connection of 3 wires. The SM321 card is constructed so as to accept only PNP type sensors in a 3-wire configuration. Use of NPN sensors would require a different model of I/O card. The SM321 card requires 24 volts DC power to perform several functions. First, the card itself requires power to light the status LEDs, perform diagnostics, and to communicate the card's input statuses back to the PLC. Power to the card is supplied by a 20.
Okay, so PLC has to be provided an external power, and that power is required to why we need an external power for a PLC, for a IO card? Again, answer can be wrong and right. It doesn't matter. Giving an answer is something that is crucial. Class, IO cards and for its LED. More answers, class, please. You can repeat the answer also. Why I do this exercise is whatever it is important, I ask these questions and ask you to write, because these are the type of questions that can be directly asked. These are only those questions that can be directly asked. So once if you write it on the chat box, then you are going to memorize it very good. Respond, class. Apart from Adarsh Shukla, I need more answers. Operate the internal circuit components. Yes. बाकी लोगों ने वीडियो का टाइम देख के टाइमर लगा दिया क्या कि हाँ हमने देखा तो हुआ है, अब 17 मिनट बाद ही आएंगे? आदर्श, नयन, थैंक यू। कल्पना सिंह, आयो कार्ड। यस, आयो कार्ड को रन करने के लिए चाहिए। आयो कार्ड पे ही हम इसको 24 वोल्ट का सप्लाई भी दे सकते हैं ताकि एलईडीज जल पाए और आयो कार्ड को ऑपरेट किया जा सके। उसकी मेंटेनेंस, ट्रबल शूटिंग के लिए भी हमको पावर की रिक्वायरमेंट होती है। यस, करेक्ट। अंकुश, आयो कार्ड। Okay, okay. To run its different components like IO card. Okay, okay, okay. Look, IO card. Okay, okay.
4-volt DC power supply connected to
Okay.
terminals 1.
So the main thing was for you to
Two
understand
is
that
a sourcing switch.
how this particular circuit is working. for PNP switch. Okay, and another one is this, that why power is required. Okay, it is very important for you to understand these both concepts. Okay, so now I think we are aligned to it, that how a particular sensor has been switched, this NPN and PNP, that whether it is sourcing or syncing, and how to wire a particular sensor if it is sourcing or syncing. Okay, another important thing was that why we need an external supply to why we need to give an external supply to PLC. Okay, and about two switches, two kind of switches. One is maintained switch and another one was momentary switch. Okay, so I need answer from everyone. I need answer from every student. uh, I have given you an example of push button. I have given you an example of push button and type of sensors. Yeah, this one, this push button. Have you seen this push button and any example? Have you seen this push button in your life anywhere? Yes, Varun had seen it. Ankush, you have seen it. Hitender, you have seen it. Where have you seen this push button? Where have you seen this push button? Kindly respond on the chat box. Where have you seen this push button? Okay, submersible. Okay, 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 okay. So, is it a memory kind of switch or is it a momentary kind of switch? Is this a memory kind of switch? Yes, it is a momentary kind of switch, but it just gives power for that instance. But the motor, does the motor just run for that particular instance or it starts continuously? The switch is momentary. I will explain how it works. Those who have answered it apart from momentary, I will those who have answered it memory, they, that is not correct. I will tell you that why you are thinking so, that it is memory, but the answer is momentary. But now the question is that when the now the question is that when the switch is momentary, then whether the submersible that you are talking about, it starts for a single instant or it is continuously running. So start continuously. It is continuous. It is continuous. It is continuous. So my question is that how have you converted a single instantaneous output into a continuous input into a continuous output? That process is called, someone knows that what is that process called? Okay. Okay. So there is a technology that is converting it. So that technology or that technical term for that is latching. Latching. It can be done through your PLC and it can also be done through your uh, relays. Okay, that technology is called latching. We will learn about that also. Okay, okay, so these are the things that we have undertaken for now. Now just let us continue with the photoelectric sensors. Okay, now let us just continue for the photoelectric sensors now. Yeah, guys, just one. Give me just 5 minutes. Just 5 minutes. Okay, class. Let us now continue with photoelectric sensors. Okay. Now just look at the what kind of photoelectric sensors are there. Okay. We are just going to quickly review about the type of photoelectric sensors. Please be focused on the type of sensors. That what are the type of these sensors.
Photoelectric sensors are used to detect the absence or presence of an object within a specific area. They detect the object through a variety of sensing modes by emitting a visible or infrared light and waiting for a response. Advanced application photoelectric sensors can detect color, contrast, distance, luminance, and even area and dimension, but we will be focusing on the simpler universal sensors. These Datalogic S100 universal miniature sensors are capable of the three primary target detection modes: diffused, through beam, and retroreflective. In addition, there are variations of these modes which allow for fixed focus detection and background suppression. Through beam, also known as opposed mode, is the most reliable mode for detection. It is also the only mode in which the emitter and receiver aren't housed in the same unit. The emitter releases a light beam, which travels across an area and is detected by the receiver. They must be properly aligned to work correctly. Any object that breaks the path of the light will be sensed instantly and trigger the output. Transparent objects such as clear glass will yield poor results, since the beam will only be broken if it passes through a thick enough section to refract and miss the receiver. Through beams have the longest detection range, since the emitter and receiver are housed separately. The S100 through beam sensor can be placed as far as 12 meters apart. If you have an automatic garage door, you most likely have a through beam sensor running across the opening to detect if somebody is present in the door's path. Through beam sensors are also immune to dust and dirt falsely triggering the output. The entire light beam would have to be obscured by the tiny particles to register, which is unlikely to happen even in the harshest environments. All S100 sensors are IP67 rated to resist dust and moisture. Check out our full selection of Datalogic sensors at the link in the description, and don't forget to subscribe and sign up for notifications. Thanks for watching, and be sure to check back for part 2 of our photoelectric sensor series.
So now you have seen the through beam sensors. So now you can understand that how through beam sensors work. Now my question is, are the through beam sensors, the output is susceptible to dust or not? Is the output susceptible to dust or is it immune to dust? Yeah, yeah. So it doesn't matter whether there is dust or there are some hindrances, because it is not going to affect. Okay, so now you can understand that why I am dealing with these sensors, because these are the sensors that are, the number of these sensors in your industry is very huge. Okay, so if you are knowing that what kind of sensor it is, how it works, it is going to be very much beneficial for you. Now let us move to switch to another type of sensor, which is your photoelectric sensor only, but this was your through beam type, and now we are going to deal with just a minute. Yeah, diffuse type. No, retroreflective type. First we will deal with retroreflective.
In part 1 of our photoelectric sensor series, we examined through beam sensors and why they are the most reliable over long distances. Next on our list are retroreflective sensors. Unlike through-beam sensors, which have the emitter and receiver housed in different units, retroreflective sensors have the emitter and receiver co-located. Once the light is emitted, it will travel across the detection zone and bounce off a prismatic retroreflector. The receiver will then detect that the light has returned. Once the light beam is broken, the sensor will indicate that an object is present. What makes retroreflectors unique is that they will always reflect waves directly back towards the source. This makes alignment easier, as the sensor doesn't need to be perfectly perpendicular to the reflector. What if something shiny passed by and reflected the beam back to the sensor? A standard retroreflective sensor wouldn't be able to see or detect the object, but a polarized retroreflective sensor could tell the difference. Normal, unpolarized light oscillates or vibrates on multiple planes. It's unpredictable and non-uniform. To create linearly polarized light, the vibration of the electric field and magnetic field must be perpendicular to each other. When we take the average of these two fields, we could draw a new vector which represents our light wave. As you can see, our light wave is now oscillating on a flat plane, so it is linearly polarized. If our sensor emits linearly polarized light, which is oscillating on a vertical plane, that light will travel across the detection zone and bounce off of our retroreflector. When this happens, the polarization of the light will rotate 90 degrees. Our light wave, which was vertical, has flipped horizontal and makes its way back to the receiver. The receiver is trained to look for polarized light, which is 90 degrees rotated from when it was emitted. When this happens, the sensor knows that no objects are present within its sensing area. So how do you tell when a shiny object enters the sensing area? When polarized light bounces off of a reflective surface that isn't a retroreflector, the orientation of the polarization doesn't change. A vertically polarized light would remain in that orientation as it made its way back to the receiver, and would be invisible to the receiver since it was only looking for horizontally polarized light. The only reflective object that could fool the sensor would be another retroreflector. The standard S100 retroreflective sensor has a sensing range up to 7 meters, with the polarized short and long range models offering a reduced maximum range of 3 to 5.5 meters due to the light loss of the polarized filters. Check out our full selection of data logic sensors at the link in the description, and don't forget to subscribe and sign up for notifications. Thanks for watching, and be sure to check back for part 3 of our photoelectric sensor series.
So now you understood the advantage of retroreflective sensors. What is the kindly answer on the chat box that what is the advantage of retroreflective sensors from the through beam sensors? What is the advantage? Is there any advantage of through retroreflective? Shiny object detection. Yes, shiny object you can say, but what about the transparent? What about the transparent ones? Shiny object can also be detected from through beam, I think. Yes, its reflection is independent of orientation. Yes, it is correct. Was there something related to distance? Just listen to this line also. Let me repeat.
Sensors. Unlike through-beam sensors, which have the emitter and receiver housed in different units, retroreflective sensors have the emitter and receiver co-located. Once the light is emitted, it will travel across the detection zone and bounce off a prismatic retroreflector. The receiver will then detect that the light has returned. Once the light beam is broken, the sensor will indicate that an object is present. What makes retroreflectors unique is that they will always reflect waves directly back towards the source. This makes alignment easier, as the sensor doesn't need to be perfectly perpendicular to the reflector.
Now answer my question that what is the advantage of retroreflective than the through beam sensor? Now answer this question. Class, please answer this question. what is the advantage of reflective sensors from through beam sensors? Yes, very good, Adarsh. Alignment is required. So your uh, retroreflective sensor can deal with misalignments also. Okay, so if you want a misalignment type of arrangement, then your retroreflective sensors can deal with it. Okay, rather than your through beam sensors have to be properly aligned. Class, are you getting it? Kindly answer yes or no. Okay, okay, okay. Very good, very good. Okay, okay. So I think this is enough for today. It has been a very complicated session because there were many things aligned up. I will continue in the next session because I don't want you to be overworked with all these knowledges. We will be a little bit repetitive. Shall we end the session and or shall we continue with one more sensor is left? Should we continue? Class? Okay, 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 okay. So I conclude the session for today. Okay, we will continue and I'll see you on Monday. Okay, okay. Happy weekend.